I'm Raghav. I work on machine learning at DoorDash, and I'm here to share about how we use AI to power on-demand logistics. Some of you might be wondering what DoorDash is. Others might be wondering what Logistics Engine is. So I'll start with an overview of what DoorDash does, explain a high level what AI in logistics is. Hopefully, that will give you a sense of how you could use it in your applications. And then dive into two particular aspects, two particular problems where we use machine learning at DoorDash. So first, DoorDash. Quick show of hands. How many of you have heard of DoorDash? How many of you have used DoorDash? That's pretty good to see. We are a technology company that's focused on being the last mile logistics layer in every city. We do this by partnering with local businesses and enabling delivery for them. We connect them with the delivery personnel and the consumers who want the delivery. So that gives rise to a three-sided marketplace. We started around 5 years ago with an initial focus on food delivery. That's what we would be known best for. And for those of you in New York City, food delivery is probably pretty common, but that's not the same rest of the US. It's relatively new, and it's fast growing. And DoorDash aims to be in 1,600 cities by the end of the year. And whenever I talk to my friends, whenever I hang out, and I explain them what DoorDash does and I work for DoorDash, they ask me if I can get a discount code, if I can give them a promo code. So this time I came prepared. I actually have a promo code that I'll share at the end of the talk. So stay tuned. To give you a sense of the scale, we work with more than 100,000 restaurants and work with more than 300,000 Dashers. And in 5 years' time, we have fulfilled tens of millions of deliveries. To understand how we use AI at DoorDash or AI in logistics in general, let's start with the marketplace. It's three-sided. We have merchants who want delivery. We have Dashers who help fulfill the delivery, and we have consumers who ask for the delivery. I strongly believe the best way to apply artificial intelligence in a business and to have impact is to start with your customer, really understand what the problems are, and use machine learning, AI, as a tool to solve the problems. In our case, we have 3 different sets of customers, and each with their own specific needs. Merchants use DoorDash so they can increase the reach, so they can reach more people and grow their business. They're looking for revenue. Dashers really enjoy the flexibility that DoorDash offers, so they can work anytime as they please. And ultimately, they want more money. They're looking for earnings. For consumers, it's really about convenience, so they can focus on what they really care about in their life. So this leads to really interesting problems, really interesting applications, where you can use machine learning and AI. Between, say, the merchants and Dashers, it's the code dispatch problem. How do we match the right set of Dashers to the right set of merchants? Between Dashers and consumers, it's about balancing the supply and demand. How do we make sure we have the right number of Dashers we need? How do we make sure we take in the right amount of consumer demand we can take in? And this really affects the productivity of both the Dashers and the consumers, and keeps them. It's probably like make or break for their experience with DoorDash. And between consumers and merchants, it's traditional e-commerce application. How do we offer you the best content? How do we show you the best content we have? And search ranking and the like. Not just between the marketplaces, we also have different applications particular to each customer. For merchant, we have a huge selection. There is all sorts of food, starting from like Asian food, fast food, which is probably pretty quick to make, or the other end, like deep dish pizza, which probably takes 25 minutes to make. How do we predict this preparation time? For consumer, it's more about user modeling. Like, what's the lifetime value? How do you decide promotions to offer to different consumers? And for Dashers, the most important thing is pay calculation. We have other like incentives. DoorDash actually has an effort-based pay model where we determine, based on a machine learning model, looking into the complexity of the order, how much to pay for the particular Dasher, how much to pay for the particular delivery, so that in order to make it consistent and fair for each delivery across all our deliveries. So Logistics Engine sort of sits at the center of these 3 sides of the marketplace and enables the deliveries to move around these. So it handles a subset of these problems that I outlined. So in short, it's the AI system that powers DoorDash deliveries. Let's start with the goal of the logistics engine. It's to execute the deliveries fast and efficiently. In terms of actual business metrics, that's going to be on-time delivery to the consumer and increase the marketplace efficiency, which is we want to deliver to you on time every time, and while doing so, increase the efficiency of the marketplace, which is churn out as much deliveries we can in a particular hour or particular day. And in order to actually do this, this breaks down into three different components. The first is balancing supply and demand. Let's say in Manhattan right now, we have 1,000 orders that we have to deliver in the next, let's say, 30 minutes, and we have 10 dashes. However good your rest of the system is, there is nothing you can do about this. That's a bad state to be in. And the reverse is also true. Let's say it's late night. We only have like 10 people asking for food, but we have like 100 dashes in the system. That's not good either. So setting up the marketplace is about balancing the supply and demand. That's the first side of it. The second piece is around planning the routes, sort of similar to how you would use Google Maps. How do you go from the merchant to the consumer? How do you organize these routes? And the third piece of it is matching the dasher and delivery. That's really the crucial part of it. So let's focus on it. Let's talk about this more. In simple terms, it's picking the best dasher for a delivery. Let's say we have 5 different deliveries with like certain pickup times, certain drop-off times, and we have 4 dashers. How do we figure out the best matching? With 5 deliveries, you probably can list them all out. There is 5 factorial ways in which you can do it. In operations research, it's what's referred to as vehicle routing problem. How do we route these? It's similar to like warehouse logistics problem. Think of like Amazon or UPS or Walmart, where goods are moving from the fulfillment centers to the consumer, maybe like with intermediate stops. However, with DoorDash, there are specific differences that make it challenging. The first of it is real-time fulfillment. When you order on Amazon, you probably get the goods 2 days later. So they have some sort of lead time in which they can plan and act. But with DoorDash, the orders are coming in right any time. So as a result of that, you're not just doing dispatching, you're also optimizing the supply for future demand, which means you not just decide which dasher, which delivery person to pick for each delivery, but also decide when you want to make the assignment, when you want to give the delivery to the dasher. So what makes it challenging? First is the complexity. I mentioned with 5 deliveries, you can probably list them out. But let's say we have 20 deliveries. That's, I don't know, a few 100 million combinations possible there. And that becomes, and with more deliveries, it explodes combinatorially. It's hard to list them out and like apply all the constraints. So we can't do that. The second part is time constraint. It's not just about deliveries coming here anytime you want, but it's also you have to deliver them in the next 30, 40 minutes. No one wants to wait for their food like an hour and a half. And the third part of it, frankly, the more crucial part of it is the variance. It's not just a software system. It's actually operating in the real world, which means there's a lot of variance that comes with real-world systems, say traffic or weather. And more importantly, there's a third piece of it, which is the merchant. And kitchen operations are hugely variable. Let's say there's a spike in in-house orders coming in. That's going to affect DoorDash orders. Or let's say there's a delay in like the kitchen staff being preparing the food. So that's going to delay it. Any system that you look into, it needs to take into account this variance. So how do we do this? I mentioned this is a traditional OR problem, and there's a lot of variance involved. And that's where machine learning comes in. Operations research, you give it a bunch of deliveries, you give it a bunch of dashers, and determine certain business goals. You can decide a cost function and optimize it. Where machine learning helps with it is, frankly, with all different inputs to the function. For example, you can predict the travel times. You can predict the food preparation times that go into the cost function. I mentioned balancing supply and demand. You first have to forecast this demand, forecast the supply beforehand, real time. That's many different machine learning models that feed into the system. So to quickly summarize, we have a lot of data. We start with the data. Let's say where the deliveries are, where they need to go, where the dashes are, what is the capacity. We augment this data with more predictions, like travel predictions, predictions on can we batch 2 deliveries together, and feed this all into an optimization engine, which determines the cost function, uses mixed integer programming, and the output is the dasher assignment. So for the rest of the talk, I'll focus on 2 specific predictions, which is the total delivery duration prediction and the batching delivery prediction, batching quality prediction. So first, time predictions. We make more than 10 time point predictions for every delivery, and they capture every part of the delivery process. And it's sort of really crucial to the rest of the logistics system. They sort of make the inputs to the logistics system. So you want to make sure the inputs are sound. So to understand delivery time or different predictions around delivery times, it's useful to understand the life cycle of a delivery. So mapping this back to the 3 sides of the marketplace, from the point of view of the merchant, the delivery starts when they receive an order. They're probably not going to start working on it right away. They have other orders they're working on. So there's some amount of time after which they start working on the order. And once they start working on it, depending on what type of food it is, how many items the order contains, it's going to take any amount of time before the food is ready for pickup. From the Dasher's point of view, it starts when they receive a delivery. They can choose to accept it or not. So there's going to be some amount of time before they decide to start moving towards the merchant. And once they do that, there's some amount of driving time. They reach the location. They have to find parking. Depending on the location, that's going to take anywhere from a few seconds to a few minutes. And after they do that, depending on how these timelines line up, they either have to wait for the food or the food is waiting. Even though this looks complicated, this is actually a simplistic view. Reason, there's more things that's going on there. Once the Dasher finds parking, they probably have to walk to the merchant. There's probably a pickup line outside there. And for the merchant, they get the food ready. They probably have to, it has to move from the kitchen to the counter or however the operations is. And this is highly complicated depending on the merchant. Let's say it all lines up, and then the Dasher picks up the food. Then they drive to the consumer, find parking there, deliver it to the consumer. And from the consumer's point of view, they place an order, wait for some amount of time, they get the order. So all of these time slices, let's say the parking time slice between when they get to the merchant and when they finish parking, or the total delivery time, all of these come from different machine learning models. They could vary in their complexity. Some could be really simplistic models, while others could be more complicated. Let's focus on one particular model, the total delivery time, which is quite representative of the other complicated models. So what's the goal here? When a consumer orders, when you order from DoorDash, we tell you the food's going to be there in 33 minutes, 42 minutes, whatever it is. So we provide the ETA to the consumer. And once we provide the ETA, we also have to deliver on time. So it also acts as an input to the optimizer. So what do we know about a delivery? We know the order details, and we know when the order was placed. So we know the market conditions right now. And this is really important for the consumer, for the business in terms of consumer conversion. Let's say I tell you the food, you can get the food in 90 minutes, you're probably not going to order. But if I tell you I'll get you the food in 30 minutes, you're probably going to order. So it affects business metrics directly. So this is a canonical supervised learning problem where you can use the historical data for training and you can validate on the latest data. We tried out a bunch of different models, and we have found gradient-boosted decision trees, particularly the one from LightGBM, to work the best. And the target here is like the total delivery time. You can optimize based on RMSE. As with any supervised learning model, the power of the prediction comes from the features. We use 3 different types of features here. The first one is the order features. Whatever we know about the order. How many items does it contain? What type of food is it? What's the value of the items? What type of order it is? What's the merchant? Maybe there are certain items which don't need as much preparation. So like it's just a soda. You can just pick it off the shelf and hand it back. The second set of features are real-time features. Anything that's going on in the market right now, that's going to impact the delivery time. Let's say how many dashes we have around in the system. What day it is. Is it a weekend? Is it a holiday? How's the traffic looking right now? And the third set of features are what we call historical aggregates. And these are really the most important features for our models. Let me explain that in more detail. These are features of the form. What's the average delivery time over some duration in the past by certain dimension? For example, average delivery time over the last 4 weeks for the particular store, which is, let's say we get a delivery from a particular cheesecake factory in San Francisco. We can look at all historical orders for that particular store over the last 4 weeks, look at the average times. The underlying intuition here is there are certain properties of the store that make them quick or late. Maybe a fast food store always delivers with an average time of, let's say, 20 minutes. Maybe Cheesecake Factory or like a pizza place probably takes 40 minutes on average. So we can extend this idea out to different dimensions, like a particular city. Maybe in San Francisco, the delivery times are longer than in a suburban area. And similarly for time of day, like late in the night, it's probably quicker to do the deliveries. During dinner peaks, there is high traffic, merchant variance. So the average times vary. You can extend this idea out to like average parking times or the variance in the times in addition to the averages. So this is good. We have a lot of features. We build a model. We use a pretty robust model. It's all good. However, when we did this, we quickly realized when you minimize mean squared error, it makes sure you're right on average. And that's just not good enough. Let's say you place 10 orders on DoorDash. We tell you we'll get the food in 40 minutes. 5 of those 10 times, you get the food in 10 minutes early. And the rest of the times, you get it 10 minutes late. We are right on average. We like delivered food every time right, but that's not what really we care about. Which is to say, with this model, your actual delivery time is your estimated time plus an error term. But what you really want is to deliver on time. We want the probability that your actual delivery time is more than the estimated delivery time is bounded. How do we do this? We use a modeling technique called Quantile regression. It's a technique to generate prediction intervals. And how it does this is, instead of using mean squared error as the loss function, we use what's called the quantile loss. If you look at the error plot, the nice-looking quadratic one is the loss function for the mean squared error. But for quantile loss, let's say you pick a quantile value of 95th percentile. The error function looks different. And what it does, it optimizes for the particular quantile value you pick. In our particular use case, we can pick a particular quantile value. Let's say you pick a low value. The estimated value will be really low. And your chance of being wrong, chance of lateness, is high. So you can, on the other end of the spectrum, you can pick a high quantile value. And the estimated value will be high, but the lateness will be low. So you can, say, pick 2 different values, like 5 percentile and 95 percentile, and have a model where you get 90% of time, the predictions will be in an interval. Or to say this differently, given a set of features, when you use the mean square error, you're predicting the average of the output distribution. With this model, you can predict the P95 of the output distribution, or the P5 of the output distribution. So how do you get the value of Q? We run a lot of experiments to figure out what works best for the consumer, and that's how we set the value of Q. We have a bunch of extensions we can do on this. Geographical ensembling, which is when you have a lot of markets, particularly markets with a lot of deliveries in the past, you can build a specific model for the market and then fall back to the global one. We can use embeddings. I mentioned the historical aggregates. Another way to encapsulate this would be to build embeddings for like each store or each market. Similarly, you can use near real-time aggregates. Rather than what happened in the last 4 weeks, you can look at what happened in the last 30 minutes, or what happened in the last 10 orders. Cool. So that's about the total delivery duration. I'll talk next on batching quality prediction. So why do we need batching? Or even before that, what is batching? It's when a particular dasher works on multiple deliveries at once. And mapping this back to the goals of the logistics engine, it's important because it increases marketplace efficiency. When a dasher works on multiple deliveries, that's more deliveries going through the system. And it also helps us with managing supply-demand spikes. So that's another reason we do it. Batching deliveries is pretty common in like traditional logistics use cases. Let's say you're Amazon or UPS. You're not just sending out one order at a time. The UPS truck probably has, I don't know, 20 to 50 orders that's going to a particular neighborhood. But what makes it tricky in this particular use case is, again, orders emerge on the fly. You don't have the time window to decide. Orders are not pre-scheduled. So you got to make those batching decisions on the fly. The second important reason there is food quality. Let's say you are on a ride sharing. Let's say you use Uber or Lyft, and you're shared with another rider. Let's say you are like 5 minutes late. You probably don't like it, but you're OK with it. But an extra 5 minutes in cases of food could be the difference between a hot burger and something that's cold and soggy. So that makes it challenging to decide when and how to batch. I mentioned variance and scale earlier. It only gets more complicated when you have batching. Anything that happens to one delivery has an impact on another delivery. So it's sort of the variance cascades. So how do we do a prediction on batching quality? To develop some intuition, a normal delivery would be you pick it up and then drop it off. But when you're batching deliveries, you pick up the first delivery, pick up the second delivery, maybe drop off the first delivery, and drop off the next one. There are many combinations you can do this. But let's say, in general, like this holds. So the intuition is any delay in the pickup of the second delivery has an impact on dropping off the first delivery. And that's something machine learning can help us with. The idea is you can predict whether something bad will happen with the first delivery and use it in the system. How do we do this? If you have your target as a Boolean variable, which is whether the actual pickup time is going to be more than the estimated pickup time, that's a standard classification problem which you can optimize for and use, let's say, PRAUC, which is precision recall area under the curve. It's important to both have a good precision and a good recall. And the way we use it in the system is mapping back to the chart where predictions feed into the optimization system. These can either feed in as constraints to the optimization function, or it could also be directly used as cost function. So takeaways, what do we know so far? Machine learning helps us efficiently solve traditional operations research problems. So if you're working on other use cases that are similar to this, you can use machine learning to help with the high variance in the system or with the real-time aspect of it. In particular, there is one standout technique, like Quantile regression, which is proven to be really effective. And this is pretty much the start of it. We are going to be working on a lot more AI applications in the future, trying out new verticals, preventing fraud. There's lots of it. I actually have a lot of time, so I'm happy to take questions. And if this is something interesting, if you find any of this interesting, or if you have more ideas on what we can work on, we're definitely hiring. Hit me up. My email address is my first name at DoorDash.com, or you can follow me, add me on Twitter, reach out to me there. And as I promised, that's the promo code. And if you've never tried DoorDash, this is a good excuse for you to try it out. It's DoorDash AI, one word. Thank you. I think you should go to the mic, please.
If I understand correctly, your optimization problem takes the input from the machine learning model into account. But aren't the two things in a way connected? Because in the delivery time, the length of the delivery time will depend also on which dasher I am actually assigning the job to. Because some dashers probably farther away from the solution, from the pickup place. So wouldn't that feed back into the machine learning model somehow?
It does. So, and the effect of this is more pronounced in supply conditions. So what we have to do when training machine learning models is look at all these cases and have heavy filters on what you use as training data for it. So only use cases in which the optimization system did a good job. So you're not training on cases which is very pathological, if that makes sense. Any other questions? Oh, cool.
What does your data science platform look like? Like, what tools do you actually use?
Yeah. We mostly use Python-based tools. Like our machine learning models are trained in like scikit-learn and like GBM packages. And in terms of actual serving layer, the predictions layer, we have our own sort of prediction service that we built out, which handles a lot of the model monitoring, logging, evaluation, experimentation, and such.
So you mentioned that you're using supervised learning mostly. So throughout the conference, there's a broad range of topics, and a lot of it came up in terms of neural networks and deep learning. So given where you are today, and given how fast stuff is moving, where do you see beyond supervised learning? What are some of the things you guys are talking about internally that you think can help you kind of continually optimize the problems that you're solving?
Yeah, that's a good question. I see it in two ways. One is in what problems we work on, and the other is on what techniques we use. In terms of problems we work on, we got to continue improving the existing problems that we work on, like these models to predict delivery times, these models to predict quality, and also explore new models, new avenues that I outlined previously, and like going into new verticals, new ways of delivering. And in terms of techniques, we already use, I could only talk about two things here, so I talked about the supervised models. We use neural nets. We have explored neural nets as both features to these models in terms of embeddings, and we also use neural nets to like train these models. As instead of like GBDT, we use neural nets. we have other unsupervised approaches we use, mostly in the recommendation space. We actually have a blog post. We use an approach similar to Word2Vec called Store2Vec, which embeds our stores as vectors in an embedding space, and we use that for recommendations. Those are some areas where we use like non-traditional techniques, if you may. Anyone else? Cool. Thank you so much, then. You get 5 minutes back.